Thank you very much. Let me start, as usual, by thanking the organizers for having me here. It's a great pleasure for me. And also with a disclaimer, unlike all of you, or most of you, I'm not a Polaron expert. So you might ask what I'm doing here. Well, the point is that I am experimentalist, and I do angle result for the electron spectroscopy mainly. And it turns out that ARPES is a good way to probe electron-phonon interactions in solids. So my brief today is to give you some general idea about ARPES in case you are not familiar with the technique, and show you a couple of examples of electron-phonon coupling and Polarons probed by ARPES. Here are my collaborators from EPFL. We collaborate with a group of Majed Shaghi for mainly ultrafast spectroscopies. I will not say much about that. And then we have theoretical support in the group of Nicola Marzari. And work at the synchrotron mainly at Berkeley with these gentlemen. So here's the outline of the talk. What does one do with ARPES? I will show you that one can measure bands in solids. And then also that actually one can measure other things than bands, which are more relevant perhaps to this particular workshop. If time allows, in the last 2 or 3 minutes, I may tell you something about a complementary technique, resonant inelastic X-ray scattering, which also can be used to probe electron-phonon interactions. So you probably know that photoelectron spectroscopy is based on the photoelectric effect, explained a long time ago. And at this time, actually, people realized that energy was conserved in the process of emitting an electron from a solid after shining monochromatic light on it. Now, what we do today, many years later, is to add momentum conservation. Turns out that in the process, the momentum of the electron is conserved, or at least a component of the momentum of the electron parallel to the surface of the material is conserved. And then by using energy and momentum conservation and simple algebra, one can derive information on the electronic state in the solid before the electron was extracted. Essentially, one can measure the initial energy and the momentum inside the solid. For the perpendicular component of momentum, well, there are ways to do it. It's a bit more tricky, but it can be done. But mostly, photoelectron spectroscopy works well for two-dimensional materials. If you are two-dimensional, you don't worry about the perpendicular momentum and you're safe. Otherwise, you have to work a little bit harder. So this is an idealized experiment. You have, say, a metal with a band crossing the Fermi energy at some Fermi wave vector. Now we emit photoelectrons and measure the photoelectrons at different emission angles, which correspond to different momenta. And what we see then is some spectral feature dispersing in energy, reproducing the dispersion of the band until it hits the chemical potential and it disappears, of course. If we care to sum all these results, so sum overall the momenta, then we should be able to recover the density of state, the momentum integrated density of state. Well, this is a real example. These are photoelectron spectra measured as a function of emission angle or as a function of parallel momentum. The actual system is not really important, but what is important is to see that you can really trace the dispersion of these bands and see where they cross the Fermi energy, which, by the way, I mean, it's a technicality. You may ask about it, but we know exactly where the Fermi energy is in our experiment. All right, and then actually, especially in recent years, the technology of photo emission has improved considerably. Instead of measuring one spectrum at a time, we can measure several momenta, energy momenta couples in one shot. We can put the measurement directly on a TV screen, so you see here a band. So you can tell actually that bands exist. I don't know if you believe in bands, but when you see it on TV, you must be convinced. And then, well, we can plot this kind of, the data in this kind of fashion, where here you have energy as a function of, say, kx and ky, and you do see all the bands. So with this kind of representation, you really have a very direct way of visualizing the electronic state in a material. In particular, photo emission is very good, and it's probably the best technique to visualize periodicities. So, like here, this is energy as a function of momentum of some system in the first brilliant zone, and then you go to the second, third, fourth brilliant zone, and you see that it really repeats itself as it's supposed to be, if you believe in quasi-momentum. This instead is a picture at constant energy of the same system, and you see this is a quasi-one-dimensional material, and the Fermi surface is essentially two parallel lines, and it's repeated in different brilliant zones. This is another example. This is a two-dimensional material, a free electron-like band here. You see a circular Fermi surface, and actually in this system there is some distortion, and you can see some ghost Fermi surface, which corresponds to an extra, to an added periodicity. And we can measure also emergent periodicity, like in this two-dimensional material, titanium diselenide, which has a charge density wave transition. At the charge density wave transition, there is a new periodicity, and you see that all of a sudden, this band is reproduced at a different place. It's backfolded. So ARPES shows band, shows periodicity. But actually, this is not what we measure. In ARPES, what we measure is a transition between a ground state of a material and an excited state where we have removed one electron. Now, under some hypotheses, which are actually in general verified, what one observes then is the projection of this state, where I have removed one electron from the ground state, on all the possible excited states of the n-1 particle system. Now, you can work out this expression, do a little bit of algebra, and see that this is actually proportional to a very interesting quantity, which is the single particle whole spectral function. And this is something that you can calculate directly if you have the Hamiltonian. So this is interesting. The comparison between theory and experiment works very well, because we have indeed something that corresponds very well to a fundamental theoretical quantity. Now, this is shown in a cartoon here. Here on the left, you would have a boring, non-interacting system. At each momentum, you have a delta function which disperses following a band. And in the interacting system, what you have here is the spectral function, which with all its complexities, instead of delta peaks, you have these quasi-particle peaks that are smaller, broadened, and then you have the dressing, which gives you these satellites. All right, so in particular, here we're interested about phonons. So the simplest system you can think of is a molecule, a diatomic molecule, H2. And if one does a photo emission on H2, this is what one observes. So this peak here would be the quasi-particle peak, so to speak, and then you have a progression of vibrational and rotational states that are hidden here. corresponding to the fact that when we excite the system and we remove an electron, we can leave it either in its ground state or in the ground state plus 1 quantum of vibration, 2 quanta vibration, and so on and so forth. So all this stressing can be directly measured by photo emission. And essentially, it's the Frank Condon idea of displaced oscillator. Now, in a solid, things are never so clear because you have many vibrations of different energies, and you do not excite, in general, just one particular vibrational state. So what you may observe is something like this. These are spectra of two-dimensional Fermi liquid system, titanium ditelluride, and what you're supposed to see here is the dispersion of a peak, which represents a metallic band that goes to the Fermi energy. Then interesting things happen actually also beyond the Fermi energy, but I will not tell you about this today. Let's stick to the Fermi momentum, to this particular spectrum here, which is reproduced over here at 15 Kelvin, and then the same spectrum measured at a progressively larger temperature. And what you see is that there is a broadening, which comes from the fact that there are phonons that interact with the quasi-particle and contribute to the scattering rate. And in fact, one can plot the width of the quasi-particle peak, plot it as a function of temperature. It's the blue dots, and this goes very well actually with the resistivity, the electric resistivity of the same material. And this width is actually proportional to the scattering rate, or if you want, 2 times the imaginary part of the phonon self-energy. And in this limit is pretty much linear and proportional to the lambda parameter, to the mass enhancement parameter. So we can deduce from this plot the value of lambda for this particular material. Now, there is another way which we can use to measure directly the electron-phonon coupling, not in the energy domain, in the frequency domain, but directly in the time domain. And this is in pump probe experiments, ultra-fast experiments where one hits the material with an ultra-short laser pulse, then excites the material and see the relaxation by sending a second pulse and extracting the photoelectrons. So this is an example for graphene. You have here the spectra before the pump arrives, and here just immediately after the arrival of the pump, you see probably there is some extra electrons over here. The different spectra are clearer. Where you see red is added electron. This electron go on the unoccupied part of the Dirac cone, and then progressively the system relaxes. From these results, one can deduce the electronic temperature, which is plotted here as a function of the delay between the pump and the probe pulses. And with rate equations, one can model this decay, and from this determine the coupling to the acoustic phonon, to the optical phonons, and these are the values that one deduces actually fairly small coupling in graphene. Now, oops, yes. Now, electron-phonon coupling, of course, influences the dispersion of the electronic states. So this is a very simplified picture where the parabolic dispersion of a free electron, nearly free electron material is modified just near the Fermi level, the mass is enhanced, and there is therefore a kink in the dispersion. And actually, this is observed, for instance, here in strontium titanate. You can see it very well. The dispersion has a kink at an energy, which corresponds to the phonon that is strongly coupled to these electrons. If one knows the dispersion of the band without the electron-phonon coupling, then one can determine the shift, which forms this kink, and therefore the real part of the self-energy, or one can determine directly from the broadening of the spectra the imaginary part of the self-energy. Anyway, the two have to be consistent. They're, of course, related by Kramers-Kronig. And then, therefore, one can characterize fully the interaction. Now, this is not just a case of strontium titanate. It's fairly ubiquitous. In particular, in cuprate system, there have been a lot of studies showing this kink, which may or may not be actually a phonon effect. I mean, it just tells you that there is a coupling to some boson. It may be something else, but so there are different schools or different churches about this. This is the case of graphene, which is somewhat more interesting because you have two kinks. People believe that there is a coupling to a phonon and then a coupling to a plasmon. So each one at its own energy, and each one giving a specific kink. Now, not only the dispersion is affected by the coupling, but also the line shape. The spectral function gives you the line shape of the spectrum, and therefore, as a function of the strength of the interaction, the line shape will change. These are examples taken, actually, I wanted to show this directly. Yeah, this is what you may expect to see from a coupling to a single phonon. As a function of the strength of the interaction. So moderately weak interaction, you have a strong quasi-particle weight and some satellites. And as long as the interaction is increased, spectral weight is transferred away into the incoherent part of the spectral function. And this is pretty much what is observed in this series of cuprates as a function of doping. And people believe that indeed by going towards more and more underdoped cuprates, also the coupling becomes stronger and stronger with the phonons. Now, this is another example from our own work a long time ago for a 1D Pyre system. The molybdenum Polarons, it's a molybdenum oxide, potassium doped. The spectrum looks rather bizarre. It's a broad spectrum, and well, you might think that the peak energy corresponds to the energy of the quasi-particle, but actually this doesn't really, is inconsistent with many results. And you can see what happens here when the temperature is changed from high temperature to lower temperature. So the red curve is for a good Fermi liquid. And as we saw before, the width of the quasi-particle peak is clearly reduced at lower temperature, while the spectrum of this Pyre system is essentially unaffected. And what we believe is that indeed what one sees is essentially an almost incoherent, totally incoherent spectral function. The quasi-particle peak is very small, is here, and most of the observed spectral function is incoherent from this satellite, which cannot be resolved. And indeed, there is indication from optics that in this material, the mass is strongly enhanced. yeah, this is another Pyre system. The idea is still the same. So there is a big peak. Actually, here there are two bands to two big peaks, and the quasi-particle is hidden here, the coherent spectral weight. And in fact, this is quite consistent with the fact that as a function of temperature, as one reduces the temperature through the Pyre's transition, there is a gap opening, and if we track the leading edge of the spectrum, which doesn't have any peak, well, the leading edge reproduces nicely the Pyre's gap. So indeed, these are examples of very strongly interacting electrons with the phonons. You may say that perhaps these are small polarons, which and this is what their spectral function looks like. Now, some time ago we looked at a system which has interacting electrons with phonons, but not so extreme, not extremely strong interacting system. So it's anatase, a titanium oxide. We'll hear more from the next speaker, actually, about this system. Titanium oxide, of course, is a wide gap insulator, but in fact, you can dope it. You can introduce oxygen vacancies, and these oxygen vacancies put actually electrons at the bottom of the conduction band. And there are ways to do it continuously. In fact, you can use light itself to create the vacancies and change, therefore, the number of free carriers. So this is the bottom of the conduction band. There is an electron pocket for the doped system. This is the Fermi surface of this electron pocket. And if we cut through this Fermi surface, so we have momentum and energy, this is what we observe. There is the bottom of a parabolic band, but there is something strange. There is a lot of intensity beyond the parabolic band, and also this band is much flatter. The mass is larger than what one calculates with a DFT calculation. In fact, the mass is something like 1.7 times the band mass. And the spectrum measured the Fermi momentum looks like this. This should remind you of the Frank-Condon problem for the molecule. There is a strong quasi-particle peak, but very clear, at least the first and the second satellite, and one can fit the spectrum with more satellites at the same distance, one from the other. And this distance corresponds to the energy of a longitudinal optical phonon mode. So we believe that this is an indication of the coupling of these electrons with this particular mode. Now, the spectral function, as you know, can be modeled in the Froelich model. At least the first satellite can be modeled. This has been calculated by also Barisic. So you see the quasi-particle and the first satellite. So the quasi-particle corresponds to the fact that we remove an electron and we leave just the quasi-particle itself. The first satellite would be the final state with the quasi-particle plus one phonon in the system, and then so on and so forth. So this can be modeled, and it's pretty much what we observe in the spectrum. Now, how can we determine the strengths of the interaction? Well, we have looked up in the literature this diagrammatic quantum Monte Carlo result, and there are two indicators. One is the quasi-particle peak. We can measure this intensity relative to the whole spectrum, and we have something like 0.36, and in this calculation, this tells you that alpha is about 2, Or we can look at the mass renormalization, 1.7, and in the same calculation, one would get 2.5. I mean, we don't claim to be more accurate than this, but this tells you essentially that the interaction is moderate, and we can think of the system as a large polaron, actually. Let me skip this. Now, the interesting thing here is that one can change the number, the density of carriers, and the spectrum changes in a very interesting way. Not only the band drops down from the Fermi level, because one is putting more and more electron, but also the shape is changing. Maybe it's clearer here. These are cuts at the Fermi wave vector. At low carrier density, this is the spectrum, as we saw before, and at high carrier density, well, there is a much stronger quasi-particle peak, and the satellites are weaker. And also, at large carrier density, the band is this parabolic thing, and there is a kink. Now, we tried to estimate things, the characteristic of this large polaron, but actually, at about the same time, or soon afterwards, we were very happy to see the calculations done in Giustino's group, and we hear from next speaker, which really explained what is happening. So these are the theoretical results compared to the experiment, and you will hear in a moment the whole story, but essentially what happens is that there is a crossover between a regime where you have isolated polarons and a Fermi liquid regime, and the crossover essentially happens when the energy of the plasmon crosses the energy of the phonon mode. Well, other examples of polarons, let me skip this. I think you will hear also about these systems from the next speaker, but I want to show you, since I have 5 minutes or something like that. Okay, more recent results, we have looked at lead halide perovskite, cesium lead bromine, and well, as you know, these materials are becoming fairly interesting for solar energy conversion and other applications. Now, in this kind of system, have a longer diffusion length. So the carriers have a long diffusion length, which is interesting if you want to use them for solar energy conversion. But at the same time, there is indication that the mobility is low. So the low mobility is an indication that polarons perhaps may form. So we looked at this material with ARPES. This is an overview. I should say this material at high temperature is cubic. At room temperature, it's actually orthorhombic, almost tetragonal. So what is plotted here, the red square is the projection of the cubic Brillouin zone. The black square is a projection on the surface of the orthorhombic Brillouin zone. Now, in this representation, Kx, Ky energy, you see that there is a band with the bottom at the gamma point, which disperses up and has maxima at the corner of the cubic Brillouin zone, these the endpoints. In fact, you should also, in the orthorhombic system, you should see a replica of this maxima here at the gamma point, because gamma is equivalent to m in the orthorhombic. But we don't see it to start with, and this is actually not unreasonable. What happens is that geometrically, the system is orthorhombic, so you would expect from Kittel to fold all the bands through the zone boundaries. But actually what matters is actually the spectral weight, and the spectral weight does not go with geometry, it goes with the strength of the potential. So clearly this is an indication that the potential associated to this superstructure is not so strong, and therefore there is nothing here. So this is a comparison of the result you can in high symmetry direction of the Brillouin zone with a DFT calculation. Now you could say that the DFT calculation reproduces fairly well the result, but actually if one looks closer, there is a discrepancy. So this is a close-up of the maximum of the valence band, here the points are fits to the spectral line shape that outline the band. From this fit, we can determine the effective mass. So here it's shown the effective mass from experiment is 0.26 times the mass, the bare mass of the electron with some small error bar, and it's the blue curve. Now DFT would give you 0.17 times the electron mass. So there is about a 50% enhancement of the mass in the real system. Now, DFT, Nicolas Colon has tried different tweaks to DFT. They also have done a G0, W0 calculation, and there are small changes in the mass, but nothing comparable to this big difference. So we are fairly sure that electronic correlations that may be there are not really important. They are not the ingredient that change the mass. On the other hand, one can put phonons, an electron-phonon coupling in the calculation. So what they did was essentially to use a theory recently developed in Justino's group. They have calculated the density of coupling to the longitudinal optical modes. Here it's plotted as a function of energy. And what they see is that there is a strong peak at an energy which corresponds to lead-bromine stretching modes of the lead-bromine octahedron. So at this point, they have integrated this peak and extracted then an integrated coupling to the longitudinal optical modes. They just neglected this part. And now from this, they go into the Fröhlich model. They consider the coupling to a single mode with these coupling strands, and they extract the alpha parameter from there, and they get alpha 1.8. Now, this shows that the coupling is not very strong. It's some small intermediate coupling, and so there is reasonable to say that these quasi-particles are large polarons. And in this limit, they tell me that one can use with some confidence Feynman's model, and from there determine the effective mass, which turns out to be 0.25 times the mass of the electron. So it's the red curve. It's not spot on the experimental mass, but it is close. So we consider this a fairly good agreement. And from the same model, one can determine the radius of the polaron, something like 60 angstrom, so several unit cells, and the binding energy. Now, similar results have been published recently for another lead halide material, at least a theory. The conclusions are essentially the same, except for the fact that in this material here, you have organic groups which also have librations, which add to the mass enhancement. How many? 2 minutes or not?
Yes, 3 if we...
3 minutes is more than enough. 3 minutes is more than enough to just to give you the flavor of a different experiment. It's resonant inelastic X-ray scattering. Essentially, the message is it's a Raman scattering with X-rays at a particular energy. You just tune the energy of the X-ray to an absorption edge of the material. This gives a lot of advantages. You can select the chemical element, you can select a particular transition, and so on. And let me just skip to the result. This is the energy loss spectrum, if you wish, of anatase, titanium oxide. And what you see here as a function of the energy loss is the elastic peak. This peak here corresponds to DD transitions, which are there because of the oxygen vacancies and the fact that, therefore, you have titanium 3+, D1 configuration. These are charge transfer excitations. Now, the interesting part today is this one, the elastic or quasi-elastic peak, which is reproduced here. I removed the main peak, zero energy loss, and what remains is the satellites. So you have a satellite structure, like in the ARPES experiment, which can be, well, these two spectra are for different conditions, for different polarization of the light, but essentially one has the same progression of vibrational states. The only difference with the photo emission is that the distance between two excitation is not 108 millivolt, it's 94 milli or 95 millivolt. And actually, together with the selection rules for the polarization, this tells us that it's not the same Phonon mode. The mode that we saw in photo emission was in the AB plane of the material. This one here is another known Phonon mode, which goes along the C-axis. So the message is that actually in this polaronic cloud, it's not just one phonon. There are at least two different phonons that contribute. And now one can fit quantitatively the spectrum and derive some parameter for the strength of the interaction. So in this M here is M over the energy of the phonon is something like 5 in titanium oxide, which is moderately strong interaction. And for comparison, this is another oxide, barium titanate, and well, it's a slightly different intensity in the tail, and this is something like 4. So this just to tell you that doing this kind of experiments, you can also extract information about the strengths of the electron-phonon coupling. So that's all, and well, I thank you for your attention.
Thank you very much. And I think there's already a question here. So in your comparison of the theoretical experiment on the cesium lead bromide perovskite, was the experiment done at room temperature?
The experiments were done at room temperature, yes.
The calculation was for 0 Kelvin?
Yes.
Right, but did you try to do low temperature ARPES on this?
Well, the problem is that on the insulating material, so that's one problem of ARPES. The samples charge up, and then it's very difficult to do calculate the experiment.
This material at room temperature is quite dynamically disordered, and there's another complication is whether it's a thermal disorder or correlated disorder. I think it's available. So that would change the band curvature.
That's a good point. Yeah, that's a limitation of our experiment, yes. Yeah.
There was another question. Yeah, in addition to the photon doping, you could also use doping by exposure to hydrogen atoms. That is a convenient means to put electrons in the conduction band.
We haven't done that. Conceivably, yes. The advantage of photon doping is that we can really tune over a broad window the density of carriers. We can use the synchrotron itself to illuminate the material, and then in an oxygen atmosphere, and by playing on these two things, we can really tune over 2 orders of magnitude the doping. We have not done it with hydrogen. Of course, with hydrogen, point is that you may worry about having surface superstructure, things like that. So it's a different experiment what one has to try. Yes. Which it's orthorhombic. I beg your pardon? Oh yes. The surface. Sorry, I didn't. Yeah. And the calculation were done both in the cubic and the orthorhombic phase, and the difference is very small, but the mass is slightly different.